Hello, everyone. Welcome to part 5 in our series on supervised sentiment analysis. The focus of this screencast is on the module sst.py, which is included in the course code distribution. It contains a bunch of tools that will let you work fluidly, I hope, with the Stanford Sentiment Tree Bank and conduct a lot of experiments in service of completing the homework and also doing an original system entry for the bake-off. I'd say that my goals for the screencast are twofold. First, I do just want to get you acquainted with this code so that you can work with it on the assignment and the bake-off. And in addition, I guess I'd like to convey to you some best practices around setting up a code infrastructure for a project, say, that will let you run a lot of experiments and really explore the space of ideas that you have without introducing a lot of bugs or writing a lot of extra code. So let's begin. We'll start with these reader functions. At the top in the first cell here, I just load in not only OS so that we can find our files, but also SST, which is the module of interest. We set up this variable here that's a pointer to where the data set itself lives. And then this function sst.trainReader will let you load in a pandas data frame that contains the train set for the SST. You'll notice that there are two optional keywords, include subtrees and dedupe. Dedupe will remove repeated examples, and include subtrees is a flag that will let you include or exclude all of the subtrees that the SST contains. By default, we'll include just the full examples. But if you set include subtrees equals true, you get a much larger data set, as we discussed in the screencast on the SST itself. In cell 4 here, I'm just giving you a look at one random record from this. So remember, it is a pandas data frame, but we can get it as a dictionary for a little bit of an easier look. We've got an example ID. We have the text of the sentence, the label, which is either negative, positive, or neutral. And then is subtree is a flag on whether or not it's a full root level example or a subconstituent of such an example. Since we have loaded this in with include subtrees equals false, we get this distribution of labels here. This is just a distribution of labels on the full examples. But of course, as we change these flags, we would get very different counts down here. And then something comparable happens with the dev reader, dev.df from sst.devreader with a pointer to the home directory for the data as before. And here, the subtree distinction and the dedupe distinction, those are much less important because these data sets consist just of root level examples, and there are very few, if any, duplicate examples in those data sets. Now let's turn to feature functions. We'll begin to build up a framework for doing supervised sentiment analysis. And the starting point here is what I've called a feature function. It's given in two unigrams phi. It takes in a text that is a string. And what it does is return a dictionary that is essentially a count dictionary over the unigrams in that string as given by this very simple tokenization scheme, which just downcases all of the tokens and then splits on white space. So as an example text, if I have NLU is enlightening space and then an exclamation mark, and I call the feature function on that string, I get this count dictionary here, which is just giving the number of times each token appears in that string according to the feature function. I'd say it's really important when you're working with the standard version of this framework, doing hand-built feature functions, that you just abide by the contract that all of these feature functions take in strings and return dictionaries mapping strings to their counts, or if you want to, their bools or floats or something that we can make use of when we're doing featureization. The next step here is what I've called a model wrapper, and this is going to look a little bit trivial here, but as you'll see as we move through more advanced methods in this unit, especially the next screencast, it's really nice to have these wrappers around the normal, essentially the fit function down here. So I'm going to make use of a scikit linear model called logistic regression, very standard kind of cross-entropy classifier. I've called my function fit softmax classifier, and it takes in a supervised data set, so a feature matrix and a list of labels. And I set up my model down here, and I've used some of the keyword parameters. There are many more for this scikit model. And then the crucial thing is that I call fit and return the model, which is now a trained model, trained on this data set XY. It might look like all I've done is call fit on a model that I set up, but as you'll see, it's nice to have a wrapper function so that we can potentially do a lot more as part of this particular step in our experimental workflow. So now let's just bring all those things together into what is called sst.experiment, which is like one-stop shopping for a complete experiment in supervised sentiment analysis. So we load in these two libraries, we get a pointer to our data set, and then call sst.experiment. The first argument is the data set that will be trained on. So that's like train df from before. We have a feature function and a model wrapper. And then these other things are optional. So if I leave SS data frames as none, then it will do a random split on this train reader according to train size. If you do specify some data frames here, a list of them, then each one will be used as a separate evaluation against the model that you train on this original data. You can set the score function if you want. Our default is macro F1. And then we'll return to these two options later. Verbose is just whether you want to print some information, and vectorize is an option that you can turn on and off, and you'll probably turn it off when you do deep learning experiments, which we'll talk about later in the unit. The result of all that is a bunch of information about your experiment stored in this variable. And because we had verbose equals true, you get a report here. And this is just a first chance to call out that throughout this course, essentially, when we do classify our experiments, our primary metric is going to be the macro average F1 score. This is useful for us because it gives equal weight to all the classes in our data, regardless of their size, which is typically reflecting our value that we care even about small classes if we want to do well, even on the rare events in our space. And it's also perfectly balancing precision and recall, which is like a good null hypothesis if we're not told ahead of time based on some other goal whether we should favor precision or recall. So that all leads us to kind of favor as a default this macro average F1 score as an assessment of how the model did. And here we've got 51.3. The return value of sst.experiment, as I said, is a dictionary, and it should package up for you all the objects and information you would need to test the model, assess the model, and do all kinds of deep error analysis. That is the philosophy here, that you should, if possible, capture as much information as you can about the experiment that you ran in the service of being able to do subsequent downstream analysis of what happened. And so here I'm just giving an example that we've got the model, the feature function, the trained data set, whatever assessed data sets were used, and if that was a random split of the trained data, that will be reflected in these two variables. The set of predictions that you made about each one of the assessed data sets, the metrics you chose, and the scores that you got. And then if you do dive in, like if you look at train set, it's a standard data set. X is your feature space, Y is your labels. Vectorizer is something that I'll return to. That's an important part about how the internal workings of sst.experiment function. And then you have the raw examples in case you need to do some really serious human level error analysis of the examples as distinct from how they're represented in this feature space. So here is just a slide that brings all of those pieces together. This is one-stop shopping for an entire experiment. We load in all our libraries, we have our pointer to the data, and then the ingredients are really a feature function and a model wrapper, and that's all you need in our default setting. Point it to the trained data, and it will do its job and record all you would want for this experiment, I hope, in this experiment variable here. There's a final piece. I want to return to that vectorizer variable that you saw in the return values for sst.experiment. And that is making use of what in scikit-learn is called the dict vectorizer. And this is really nice convenience function for translating from human representations of your data into representations that machine learning models like to consume. So let me just walk through this example here. I've loaded the dict vectorizer, and I've got my train features here in the mode that I just showed you, where here we have two examples, and each one is represented by our feature function as a dictionary that maps like words into their counts. It can be more flexible than that, but that's like the most basic case that we consider. When I set up my vectorizer in 3, and then I call fit transform on this list of dictionaries. And the result here, xtrain, is a matrix where each of the columns corresponds to the keys in the dictionary, representing a unique feature. And the values are, of course, stored in that column. So this feature space here has been turned into a matrix that has 2 examples, 0 and 1. There are a total of 3 features represented across our 2 examples, A, B, and C. And you can see that the counts are stored here. So example 0 has 1 for A, and 0 for and 1 for B, and 0 for C. And example 1 has 0 for A, 1 for B, and 2 for C. So that's recorded in the columns here. You can, of course, undertake this step by hand, but it's a kind of error-prone step. And I'm just encouraging you to use dict vectorizer to handle it all and essentially map you from this, which is pretty human interpretable, into this, which is something your models like to consume. There's a second advantage here, which is that if you use a dict vectorizer and you need to now do something at test time, you can easily use your vectorizer to create feature spaces that are harmonized with what you saw in training. So as an example, if my test features are another pair of examples with a different character, then I can call transform on the original trained vectorizer from up here, and it will translate that list of features into a matrix. Now, the important thing about what's happening here is that it's going to package the test features into the original training space, because of course, those are the features that your model recognizes. Those are the features that you have weights for if you've trained a model. So it's important to call transform at this space. And as an indication of one of the things that's going to happen here is, notice that in the test features, my second example has a brand new feature D. But D is not represented in the training space. We have no weights for it. It's simply not part of that original training data set. And so the result is that when we call transform, that feature is simply elided, which is the desired behavior as we're translating from training into testing. And notice that the dict vectorizer has simply handled that seamlessly for you, provided that you remember at the second stage not to call fit transform. That's the number one gotcha for this interface, is that if you call fit transform a second time, it will simply change the feature space into the one that is represented in your test features, and then everything will fall apart, and your model, as trained from before, will be unable to consume these new matrices that you've created. But provided you remember that the rhythm is fit transform and then transform, this should be really a nice set of interfaces. And of course, this is what sst.experiment is doing by default under the hood for you.